Very glad to be here before you today. Let me first see if I can set up a pointer. Oh well. Sorry. So I'll be talking a little bit about how to model music, and really how do you measure if you're able to successfully model music. The most advanced application of that would be to actually be able to generate music, because if you're able to generate music correctly or well, then that would mean that you were able to successfully model the music. Now, as Prof. Yuang said before, I am from SUTD. I'm an assistant professor there. Before I worked in music in London. You might be familiar with that if you've read some research papers on the topic. There's quite a big research group on music technology there. And before that, I was at the University of Antwerp, where I did my PhD. So I'll be talking a little bit about, I want to start with a sort of history of how people have been trying to generate music automatically. She likes it. Sorry. And by listening at some of these early examples of music generation, you'll see that there's some limitations to naive, simple modeling methods. And then we'll kind of move into, throughout history, how people have been modeling. Rule-based approaches to machine learning approaches, getting ever so advanced. So let's just start with this history on generation systems. So I've listed quite a lot, actually. You might have heard of this one before. The musical dice game. Anybody of you is familiar with this one? So Mozart would be the first one that people believe who actually did a sort of music generation system. How did he do that? He'd have little bars of music labeled 1, 2, 3, 4, 5, 6. You'd roll a dice, and then your composition would be based on what you rolled with the dice. Okay, the Musikalisches Würfelspiel, they called it. Now everybody thinks it's made by Mozart, but it's actually made by Johann Philipp Kernberger. Okay, and it was made to style music. So how does that look like? Just to kind of give you an idea. From Kernberger, he has a sort of sheet of music with the bars labeled 1, 2, 3, and so on. There's more than 6. How does that work? You have a sort of very naive version of a transition matrix, almost like a Markov model. And he says, well, if you roll this dice and you're currently at bar number 5, then switch to bar number 3. Okay, so and you get to create a whole piece like that. Okay, I think I have an audio file just so you can hear how it sounds. I mean, sounds pretty decent. Of course, they're not really generating music. What he has as units are whole bars, which obviously sound pretty good. They're all in the same key, and the only thing he has is the transition probabilities between one bar, not looking back at any of the previous ones. Okay, but still, kind of cool that they did this back in the 1700s.
How do they compose the bars?
Well, that's because they're composers.
Okay.
They can compose the bars. They call these things chance-inspired generation systems. And there's been a bunch of other ones. For instance, we have John Cage. You might know John Cage is also a composer. For instance, he took a star chart and then he decided to put empty musical bar lines over it, like the 5 musical lines. And wherever there was a star, he would say there's a note. Okay, that's it's an interesting way. So this piece was called Atlas Eclipticalis. If you listen to it just briefly at the beginning, you'll see how it's actually very avant-garde. It sounds very random, as you would expect, of course. But just to say that not all music is actually very structured. Okay. So when we think of how do we model music, we're usually looking at, let's say, Western music or Mozart, Bach type music, which is very structured. There's a bunch of other of these avant-garde composers who've done things like this. There's Charles Dodge, another composer. So they're not computer scientists, of course. Oh, actually, this could be. He made a composition called The Earth's Magnetic Field. So he just assigned sounds to a recording of magnetic fields of the Earth. Okay. Also sounds very random. And it's nicely sounded electronically as well. Okay, so these are very, I'm not especially a fan of avant-garde musicians, but it's worth mentioning that they've come up with these ways to model their music. You must be familiar with her. Yeah, I see some of the ladies here really shaking their head. This is Ada Lovelace, who's considered to be the world's first programmer. Yes, programming used to be a women's job. Basically, women. Yeah.
Programmer.
Yes. So she was the assistant of Charles Babbage. If you know him, he made the difference engine, and it's like a calculator but running on a steam engine. And she was the first one to write these punch cards for the machine with the programs. Okay. So Ada, when she was making the notes of this engine and what the engine could do, and when she was envisioning computers to be able to do, she wrote this. So the engine's operating mechanism might act upon other things beside numbers. And she said, in particular, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. So there you have it. The very first computer was already, they were already thinking about, let's use this for music generation. Okay. So if anybody ever tells you, why are you doing music generation? It's like, they've been doing this since the birth of computers. But that was good in theory. They actually never did music generation on this engine. That happened later. The first computer-generated piece, it's called the ELIAC suite. And it was composed on the ELIAC computer, which is this one here. Now, if you're familiar with the history of computing a little bit, this is a huge machine. I don't remember how much memory it had, but it's countable in the megabytes, right? They had to program this computer by putting patch cables between the different inputs. So quite the job. So what these two people did, Hiller and Isaacson, is they made a statistical model that could compose music. It was based on Markov models and some rules. And they managed to implement it, and the resulting piece is a string quartet. I'll play it for you. So you might say it's not perfect yet. I mean, depending on what style you're going for, of course, that's always a question. What's interesting also to notice, if you look at the score, they have 4 instruments, but they're a little bit cheating, and they're still doing melody generation. Yeah. But this is a really interesting start of the music generation era. Oh, sorry. If we move on through time from the 50s, we actually get quite some interesting compositions. We have composers like Yanis Xenakis who actually try Markov models, like Lejarn already did, and their models can just be. You have all the keys of the piano. If you play this key, then you have a chance of going to that key. It's pretty simple, but also very basic. This is a first order model. Are you familiar with Markov models a little bit? Yeah. So then you know that we look at one note and then we get the probability of going to the next note without looking at any of the previous stuff. It's not gonna sound very good, right? Possibly I also have an example of this. Yeah. Oh, sorry. Well, you get the idea. It's very chaotic. Slightly different models would be fractal models of music, where you sort of inspire yourself on the representing music as numbers and following these things. So that actually sounds a little bit better, but still doesn't feel as natural as it's supposed to. Maybe good elevator music. Yeah. I don't know. Or it sounds a little bit Chinese to me. I don't know. Yeah. Maybe it's the instrument. Yeah. Anyway, so we're getting closer to current days. David Cope, very famous automatic composer, kind of, also a real composer. David Cope did something in the 80s called Experiments in Musical Intelligence. And that was basically, he was creating a bunch of models that came from a composer's block. So he was stuck, he's a composer, he was stuck, and he thought, maybe I'll just model how I think about music. And then he was able to write. He also did this for other composers' styles. So for instance, he wrote this Chopin Nocturne using a model of Chopin's music. So it sounds very much like Chopin. However, there is a pitfall here because we are researchers. And whenever we do something, like personally, I write it down in a research paper so other people can replicate it, which is considered good science. David Cope, if you read any of his books, you'll see that it's very vague. So there's no real way of telling what he did as a composer to augment the music that was generated and what the model did, or even how the model looks. So while a lot of people, if you ask them about music generation, they'll be like, but Cope has done it. But we really don't know. So, in recent days, there's been a lot of progress. I'm almost through the examples, but I want to show you some real life system. So all of these systems that we saw, you press a button, it generates a whole piece, and then you play it. There are some systems that work interactively with the performer. So for instance, Francois Pachet's system, for those of you who are familiar with Pachet, so he used to work at Sony Computer Science Laboratories in Paris for the longest time. Recently he switched to Spotify, where he's director of creative technology system. So maybe thinking that Spotify might be doing some music generation. And one of his famous systems is this continuator. It's a factor oracle, if I'm not mistaken. Oh no, it's a Markov model. Works in real time. So we don't pre-train it on a corpus. The Markov model is learned or trained while you're playing. So at first it's inside bars. And that's the first thing that fills up the model. You play more and it fills up more. So that means that the system is going to be playing with you and mostly repeating things that you've already played. So I put a video here. Let's see. I don't know how long it takes to start. Let's, okay. So you see how the person played a scale, and then the machine actually repeated the scale higher in the octave. So that's actually a sign that the Markov model has not been trained on pitches. However, it's been trained on intervals. And that's something that people often do. So instead of saying, if you hear this pitch, play that pitch, it's trained on the fact of if this interval was played before, so from this pitch to that pitch is maybe a whole tone, then do the next interval. Okay. So that's kind of a way of getting around the fact that your data set might contain different keys. Mm-hmm. If you don't want to make models built on intervals, then you have to transpose all your pieces to C major, for instance. That would be a way of compensating. But using intervals is a good way of actually taking into account the last two notes versus just only the last one, while still having a first order model. I'm going to say a little bit about this later on, but there are some, if you want to work with Markov models, or basically any statistical model, there's a paper by Darrell Conklin in the 1980s, and it's talking about multiple viewpoints. Multiple viewpoints are multiple ways that you can see musical piece. So pitches are a first viewpoint. Intervals would be a second viewpoint. Then you would have harmonic intervals. You could represent a note by, this is on the third beat of the measure. You could just count the number of beats it's on from looking at the meter. That's a bit harder to calculate from MIDIs. Or you could look at the duration of the note. Also important, if you're generating, you're not just generating pitches, you want to generate duration. And you want to look at, what else do they look at? What degree of the key is it in? Is it the dominant note? Is it the tonic note? For those of you who know a bit of music theory. Okay. So I think 1985 or something, the multiple viewpoints is a really good reference. I can list a few, but there are like 120 features that you might use for this type of modeling. Okay. Mimi, I won't show you the video, but Mimi is basically very similar to what we heard before, but instead of just hearing what the computer is generating, you actually see the piano roll coming, so you can anticipate what the machine is going to play and really play together with it. Okay. Now, there's some software available that you could use to sort of implement your things. There's Bob Keller's work, which basically has you can download Improviser, and it has a sort of plug-in system where you could implement your own Markov model or whatever you want to do. If you look at the menu currently, you already see that you can generate using this probabilistic model, this or that. So it's kind of cool to see what's out there and easily testable in chords mostly. Okay, but
is it open source?
This actually, I have to check. Bob Keller is a very nice guy. He might be able to be he might be open to sharing within the labs. I'm sure he would be. The software itself you can test open source. I mean for free. So then these days, we're getting to a point where I think there are 3 sort of serious startups that are doing music generation. One of them is JukeDeck. You can just go to the website and give it a go. It actually sounds pretty nice. Although I must say that mostly it sounds nice because they still enforce a lot of rules by hand. So they have a team of composers working for them. Resources on making the sound nice. So they do a lot of production tricks, mastering, and all that automatically. But you go there, you say, I want rock music, I want it in this mood, and so long, and then it makes you clip in a few seconds. So you can give it a try. Mostly this is, let's say, some drums with some guitar strumming and a little bit of a melody on top. The melody being the one that's the hardest, obviously, to generate. Okay. Overview of where we are at in music generation. Now, does any of you have like a music generation app that they listen to? Well, okay, that's great. I think I've been always asking this, and it's only occurred once that somebody was like, yeah. So, with all these efforts from the 50s, people are not listening to automatically generated music. So to me, that means that it's not good enough yet. Okay, and I think for mainly two reasons. So the music doesn't have structure in it. Whenever I like listening to a song, it needs to have something that sticks to my mind, like an earworm, something repeated. And I think that's what is hard to get in the music. And then, secondly, music is very much connected to the emotional. So if you break up with your boyfriend, you want to listen to some sad music and just, it's very much connected. So machines are not good at emotion. Right? So we need to find a way to guide the emotions through music when we generate. And I'll talk about how I incorporate these two things, the structure and the emotion, in my research later. I already mentioned that there are rule-based methods and more statistical models, and I'll go over all of these in more detail. So I shouldn't convince you guys that the digital music is rising rapidly. I always have this slide to convince people who are not in the field that we have a lot of new applications. Again, you guys. First, the naive approach would be to use, if you're going to model music, to use rules from music theory. You can do that, but only for certain musical styles. Okay? And if you read any papers, especially from the 80s and 90s, you're going to see a lot, and actually still today, you're going to see a lot of people working with counterpoint or chorales or something. This is because it's basically the only musical style that has rules. Okay. In fact, counterpoint has 5 species, and it was developed as an educational tool for composers. So it goes from easy to hard. Now, in my very first research for my PhD, I thought that composing music could be a combinatorial optimization problem, whereby we say we want to find the right combination of notes so that the music sounds good. And music sounds good if all the rules are, it's just constrained programming almost. So what I did first, I wrote a little formula for each of the rules of counterpoint. An example rule: if you do a large leap, it should not be filled with another large leap, but it should have stepwise motion in the opposite direction. Okay. Rather straightforward rules. I wrote all of these down. In fact, any of you interested, I have the C code for this. And then it's actually pretty simple. I use a meta-heuristic to make sure I find a combination of notes that satisfies all these rules. And if you're familiar with meta-heuristics, it's not an optimization class, so I won't go into detail, but meta-heuristics, you might know genetic algorithms. Personally, I used a search-based heuristic, which is variable neighborhood search. How does that work? I just start with a random combination of notes, and I make small adjustments so that until my objective function is minimized. quite straightforward. We swap moves, we change the pitch of one note, change the pitch of multiple notes. These are our moves. There's a sort of flow to all of this, whereby if our search gets stuck, we sort of perturb or we switch move types and we manage to go on. How does this end result sound? Now be aware this is a MIDI file. I should have had somebody play it on piano. And it is counterpoint music, but it sounds like this. Okay. Right, so hopefully you find it passable. So while this was an interesting experiment to do, nobody really wants to listen to this music. So and for pop music, we don't really know the rules. So we need to switch to machine learning. However, the simplest thing in machine learning would be right. Now the thing with the Markov models is, of course, that that the larger structure is still not really adhered. Okay. Now I'll talk about this in a second. So, for instance, if we have something that has a verse and or certain repetitions in the structure, you can't really tell the model do this or do that. So it's a big constraint. It's also something that François Pachev at Sony's been working on a lot. Another issue with Markov models, and it's actually a design issue more, if you make the order of the model too small, you don't get any repetitions and it doesn't sound good, as that example we heard earlier of the composer in the 50s, which had the piano keys on the matrix. If you make the order of the model too big, you're going to be plagiarizing existing composers. Okay? If I take as order of my model 2 bars, that means I'm going to train the model on a data set of songs. That means I'm going to take literally 2 bars out of an existing piece and put it in my own. That you can't really do that. You might have some trouble, right? So there's a delicate weighing to be done between plagiarism and length of the matrix. There's been, if you're interested in that issue, there's actually Papadopoulou has written a whole paper on that issue. I've already mentioned the viewpoints by Conklin. Oh, the paper was I had an earlier paper about the multiple viewpoints. Okay, but for this little test, we took, I think, second order counterpoint, and we looked at three viewpoints. Okay, so we represented this type of music with the interval between these notes plus 5 semitones, interval between them vertically 3 semitones, and the interval in the baseline 2 intervals. Okay, so it's a very simple representation. We just wanted to see what gives. The issue that we found, however, is that if we use this first order model, and our data set as we're working with music might not be too big because we need MIDI, we don't need audio, the issue is that sometimes it becomes very repetitive. Okay, so in order to examine this a little bit further, we developed a solution for this. I'll illustrate it in some research we did with rather strange music, which you might not be familiar with. Anybody know this instrument? I didn't either before I met my collaborators. It's a bagana, which is an Ethiopian lyre. It only has a few notes. It's very a sort of droning music. Here's our master playing it.
From which country?
Ethiopia. Ethiopia.
Oh.
Yeah. So we met with somebody who did their PhD on studying Bagana music. And we decided to model this particular music. Why? Because it has this sort of structure that I mentioned earlier, where you have, for instance, A2 structure being repeated later, this whole segment being repeated, which is hard to control just by using Markov models. So we wanted to try to look at this as also an optimization problem, whereby we somehow integrate the Markov probabilities in the objective function. So we could, for instance, try to choose the notes such that we have the highest probability all the time. Okay? Would that be a good idea? We could constrain the notes so that they match regular expectation profile or not. We've tested it. You'll see it on the next slide. So based on this music, I'll show you two outcomes. First is these high probability sequences. So we can measure probability using the cross entropy. So that's the inverse of the probability. It's not good. If we choose the highest, the most likely note at each step, we get something very, very repetitive. I know for us it sounds maybe similar, all because it's unusual music. So what we did is we actually found 5 experts in Bagana music. We let them listen to all this and they rated the music. This one wasn't very good. So now what we tried to do is we have our Markov model based on our corpus of Bagana music. We built a second Markov model on this generated fragment. And then in our optimization, we tried to minimize the distance or maximize the resemblance between the two statistical models using KL divergence. So that was actually seen as the best way. Now, I know if you would have a very long song and you would just generate out of the Markov transition matrix, you would get something similar. But by doing it with optimization, we are able to take into account, for instance, these constraints. The fact that after this note, sometimes there need to be this note again. So this is all taken into account. And we managed to constrain the fact that this needs to be here. So there's some advantages to doing it this way. The obvious disadvantage would be it takes a lot longer to generate. Okay. Oh, this is how the okay. So this, I know, is very particular music, but sometimes it can help you create your models just by sort of reducing it to the basics. Right, so let's get back to our main challenges in the field right now. So we have these two issues. How do we constrain structure? How do we put in emotion? I try to address these two issues in my work on Morpheus, which you might have heard of. I'll talk about Morpheus and then I'll talk about more recent work on LSTMs and Word2Vec. So I think should have enough time. First of all, emotion. How do we even model emotion in music? A model that captures tonal tension. Tonal tension is important because, let's say you have a video game, you have a tense moment, you need to be able to steer that. I used this model by Elaine Chu, which is a spiral array. Basically has 3 spirals or 3 helixes, and each one has spatial coordinates of pitches, chords, and keys. So we are able to represent all of the notes of a piece as a sort of cloud in this array. In this small example, the first chord, C, E, G, can be represented in the array C, E, G. Okay, very close together. So these are fixed positions that Professor Chu has determined. The second chord, which is a diminished C, I think, yeah, can be represented as such. You see a difference between them, right? This one is way more stretched, and if you'd play it, it sounds a lot more unusual or strange, maybe tense to us. So that's one way that we could represent tension in music. We've devised two other possibilities. First of those two others would be the change or the movement between two chords. So if we have one chord, this first one, we move to the second chord. It's quite a big change if we look at the geometrical center. And then we move to an inverted chord, which is represented as the exact same one, so no change there. So we can also give us a different way of looking at tension. And then finally, we can look at how far are these chords from their key. The key of C major is here, also a coordinate determined by Elaine Chu. Also this you can easily get, there's MATLAB and Java code for getting these coordinates. Here is here, it's very close to the C key. The A minor chord still close to the C key, as you would expect, and the C sharp chord far away. So these are very clear ways that you can take a chord and see how tense it is. It's an example here, a very famous tense chord called the Tristan chord, which comes from the opera Tristan and Isolde from Wagner. And each time the character Tristan comes on the scene, this chord is played as sort of to indicate this tense moment. If the chord is extremely stretched out, so this indicates something. The three metrics are displayed over the scores, and you can see exactly where it appears. So it's here. So this is a very clear thing. We have this also as a library. It's just a Java jar file. You can access it and get the three metrics right away. Second issue, the structure. Long-term structure in pieces can be detected. If you're familiar with the work by David Meredith, you might know about his compression algorithm, which is very much inspired on the work of compressing zip files. It finds repeated patterns of notes. Here we have the notes represented in pitch, height, and time. Okay. If it finds similar patterns of notes can be transposed, it will flag it. So this gives us a way of getting patterns out of a piece. Results are displayed like this, but I won't go in here detail. Maybe you see how this follows the same contour as here, so it's recognized as this red pattern here. Okay. So these two tools we'll use to generate music. First of all, we take an existing piece, so I'm cheating a little bit, and we calculate the structures. So we do the pattern detection. Then we let the user input the tension they want throughout the piece. That would be the emotion. Or we just use the existing tension from the template piece. Then we're going to erase all the pitches of this original piece and generate new ones. We start with random pitches, but we make sure that they satisfy our patterns. So if there's a theme that comes back after 3 bars, it's going to have to come back. Even if the notes are different, it'll come back. Using that, we took a very famous song, one that you all know. Right? I won't play it entirely. Oh, sorry. Won't play it entirely. So first of all, we replace it with random notes. Sounds pretty bad. And then we optimize it so that the tension which you see overlaid matches sort of with the original. This is the result. Okay, so you recognize the original piece in this, and this creates a sort of special or strange expectation, because you're almost expecting to hear the original piece, but somehow you don't. So this is an interesting experiment that shows that just by constraining the structure and the tension, you can actually already have a piece that sounds decent. This was work done by Elaine Chu, who's actually been performing these pieces at different locations, which with her great playing is able to make them sound even better than this. Okay, but let's move on to some of the recent work. So I consider what I did a little bit cheating, because we used this existing piece to get the patterns. And in theory, the machine learning algorithms should be able to generate these repetitions. So the obvious choice that we're looking at is RNN-based models. You're familiar with neural networks a little bit, I think? Yeah? So, you know LSTM. A more efficient form of recurrent neural networks. And we thought it would be good, because we're trying to capture long-term structure, it would make sense to use RNN models. Now, in addition, we thought, well, CNNs have sort of transformed the field of vision. Look at the ImageNet competitions, how the accuracy's gone up like that. I think it's time that the field of music also has this boom increase of accuracy, hopefully also in music transcription in a few years, because then we'll be able to have great big data sets for generation. So we were hoping to combine these advantages of CNN with the LSTM. So we've made an image-based representation of music to be able to combine both of them. Now there are some examples that I'm sure you've seen if you do some research. There's a famous paper by Boulanger and his co-author which uses piano roll representation with an RNN recurrent Boltzmann machine. Okay. So this was kind of a breakthrough paper, because they were the first to do this combination. And what's even more, the RBM is very efficient if you take if you have low data, right? Because it represents your data as distributions. So it allows you to be more efficient in that regard. And it's probably something I should use in this particular research too. But so this combination of piano roll representation has been done with other networks. For instance, it's been combined with RNN in Siddharth Sitkha's paper on, sorry, I didn't put it on here, but this was on automatic transcription. But piano roll seems like sort of a limited representation. So we thought, why don't we look at music theory? How do they represent music there? Very famous representation is tonets. Not sure if you're familiar with this type of thing. Tonets represents music spatially in such a way that the relations are meaningful. Let's say we'd have a fifth going down right. We have minor third, how do you say that in English? Going right up. You have a fifth going right, a third going down, sorry. So we would expect that if we put a CNN on there, it would be helpful for the CNN that the locations are more meaningful. So one thing we did, we adjusted this a little bit. We thought there wouldn't be really a use of having it like this, so we made it straight. And we therefore transformed it into a matrix. Another adjustment we did is because this tonet often goes without octaves, we added octaves to it. And the result can be plugged into this network. You have the TONET's images, so an image for each time frame. I believe we took the smallest beat that occurs in the music. This is based on MIDI files, and we created an image of it. Well, not really an image, but we represent it in a matrix in a 3D matrix, basically. Fed it to a 2-layered CNN, the usual CNN, so with max pooling and yeah. What else did we do? We did 3x3 filters, fairly standard CNN. Then the output of the CNN we fed to an LSTM network with 3 layers. Okay. So we're hoping to both capture the spatial relations in the music and also get the time element structure in the LSTM.
So this is published in Triple AI.
Yes. Yeah.
Full paper.
Full paper. Yeah. Thank you. Yeah. So this was just paper published this year. So if you're interested in reading details, you can. Also, the software should be available here. The only thing we're still working on is the pre-processing of the MIDI file is currently done in MATLAB. We're trying to make it easier so it's all in Python, the rest is in TensorFlow, so you can do it in one go. If you have any questions if you want to implement this, you can just ask me or my co-author Chinhua Chang or Huang, yeah, and we'll be happy to help you. So what do we see if we do this? First of all, we look at some of the filters. The filters of the CNN sort of show us that we capture spatial, or we capture tonal relationships. What these filters are filtering out here, for instance, is the 5th relationship. Right? Vertical, gosh, I have to think a little bit, but vertical relationship was a 3rd, I think, a 3rd. So that's very interesting to see. So it does mean that inside the CNN there's sort of efficient representation happening for musical features. What we did is we generated music using this TONET's LSTM, and then we replaced the TONET's by piano roll, and we compared the results. What we did was we calculated the tension of the pieces. This would be the average tension per piece for the piano roll and the TONET's, the 3 different tension metrics. And on average, we saw that there's much less tension in the TONET's generated to our system pieces. Tonally more stable. Okay, there's less weird things in there, which we think is a good thing. Another thing we did, I didn't put the table here, you should check the paper for the full table, but we applied David Meredith's algorithm again, the pattern detection, and the pattern detection algorithm gives us the compression rate. Right. Just like if you're compressing a zip file, if there's a lot of patterns or themes found, then the compression rate is going to be high. So what we found is there are significantly higher compression rates in our system versus the piano roll, meaning that there should be more themes and repetitions in these songs. Here's one example. I just took one at random just before class, so we'll see. I must actually warn you about something. What we didn't do is take duration into account. Okay? So these are all very equally duration notes, which might make it sound a little bit strange. We're actually doing this right now, so we're improving the system. It's pretty simple, it's just adding an extra bit to give the duration. The results with piano roll, they're also not bad. But they have a little bit more irregularities, so a little bit strange notes that don't belong to the key. Okay. I just took two out of these. They're very different pieces. This is monophonic. The algorithm will just generate differently each time. Right? Sometimes there's one melody, sometimes it's like the other piece, which has more notes. So if you're interested, you could go to my website and we have some more generated pieces on there. Okay. That leaves the last project I want to talk about. I know we don't have much time. I'll try to. Okay. So, which is inspired by natural language processing. Mm-hmm. You're familiar with the model called Word2Vec by any chance? Yeah. Which is one of the word embedding models. What word embedding models do is they take a word and they translate it into a vector of numbers, basically. Why is that? Because machines are better at processing numbers. There's a very famous example, but if you've had a course, you've seen this example. The gist is basically that the distributional semantic hypothesis says that words that are used together and occur together in sentences basically tend to have similar meaning. Mm-hmm. So the entire model is built on this. Words that the algorithm finds in the same context will be in a similar place in this multidimensional vector space. So the model takes one word and puts it in this multidimensional space. It gives it a location. And we can sort of assume that if words appear close together, they mean the same thing. Mm-hmm. What's more, there are these cool things in the space that, and that's this famous example, I don't know if you can see it. If you'd have a space based on normal words, so not music, and you have man, woman, king, and queen, if you translate from man to woman, the exact same vector translation, if you start that from king, it'll end up in queen. So that's pretty cool. So this means that this is really a useful representation. So music and language are very similar. Okay. There's a whole paper describing how similar they are if you're interested, Besson and Schoen. And the interesting thing is that actually both language and music came from the same evolutionary reason, which is emotion. So again, the emotion. We do a high shriek or a shrill sound if we're afraid or being attacked, and that could be the fact that we use different tones results in singing, but it's also sometimes we use words to express our fear. So both are related in that way. They have temporal ratios, a sort of grammar, meter grammar. They have a rhythm, and both have very strong expectancies. If I sing happy birthday and I wait, I don't sing the last note, you're really going to want me to sing that last note. And the same goes for language. If I say tonight I'm going to have pizza from Domino's, well, pizza, you expect me to say that last word. And a similar mechanism in your brain goes on between music and language. So I decided to try these models on music. There's been some other research on this, but very limited and mostly about chords. Anna Huang, who's an intern at Google Brain, did some work on chords. I think it's called chord ripple, whereby the chord label is just a word. We did it a little bit different. We took a musical piece, we sliced it up, and each slice, is just a bunch of notes, and each slice like this in a dictionary is considered as a word. So even if a slice would be C-E-G and a second slice would be C-E, so two notes in common, even in the dictionary they would be considered as totally different. So we're not taking any musical information into account. So that's how we represented our words. We noticed that in our corpus, the funny thing is, usually when music researchers train their models, they use the Bach corpus or chorales or this. We decided to use this collection of MIDI files we found on Reddit, which was said to be the largest MIDI collection in the world, and it had Metallica songs, it had everything in there. Okay, so we decided that would be a challenge, and we found that there were over 4,000 different words, so slices. And as you usually do if you have a word2vec model, some of the words that are only used once are not worth modeling because you make it too difficult to train your model. So we cut off here. These are all of our slices sorted with their occurrence. Okay. We only kept the first, or the 500 most occurring, which is about 10% of the corpus, which is a fairly standard rate. When we do this, we have our data set. We give a label to all of these chord slices. We call it word 1, word 2, word 3, and we just get into the realm of NLP again, because now our music is transformed into sentences. And we use word2vec. So it's not a neural network class, but instead of word2vec, you could have used GloVe or something else. There's a bunch of alternatives. Word2vec, because it's very quick to calculate, efficient model to run. So it goes, even this complex model goes in a few minutes, which is pretty amazing. Word2vec, just a small reminder, it's a 2-layered neural network if you don't count the output layer. Input word, you have your projection, your hidden layer, which will contain your embeddings later, and your output layer. Output layer would be the surrounding words. So you're trying from your current word to predict which words will be around, surrounding it. In order to do that, you have to decide on how big your window is. So how many words are you going to look before and after your current word? Those are some of the hyperparameters. We think 2 window size was the best, but I'd have to double check. So it's really fast to compute. Now, does this capture anything meaningful? So remember that this model did not know what was in the words. They were just dummy words, labeled word 1, word 2, etc. Now, if we represent, sorry, if we look at the distance between all of the chords that we label as, let me look at it for a moment. Okay, all of the chords, like the 4th and the 5th chord of a key. In this case, we looked at pieces in the key of C, and we looked at the distance of the piece center with the chords that were like their dominant tonic chord. We saw that the chords that belonged to the key in a musical sense were much closer to each other. Okay, so that's very interesting. It means that without even telling them what chords it were, the model is still able to capture it. So here you just see the evolution of those distances during training. So you see that the model goes from bad to a much better. The strange purple line here, for instance, is a 2 flat chord. Not even sure what that means. I think from C major it would go to D sharp. Very common chord, so hence the distance is also really big. We looked at some other things. For instance, we took the well-tempered clavier pieces. Why? Because they have a piece in every key. And to get more data, we even transposed them into all keys again. So we had the same number of pieces per key. Then we looked at, I think, you remember, it was the key of each piece, and we took the center of the piece. And then we noticed that pieces that are a fifth apart, for instance, from, I know it's very small, from C to G, have much smaller cosine distance. So again, it's an indication that these tonal let's say, intervals are captured by the model. You capture the cosine angle, the angle between the vectors, and this angle, you could sort of see the circle of fifth in the angle, because it's always the same between each of the keys. So this, to me, is quite promising, and I would actually very much like to integrate this and use it to even replace the tonets. Now we have a representation that we can use for music. They're just numbers. So we can translate these, take them, put them in an LSTM, and see what it would give. Yeah, and then we can experiment all these things, see if we can use it to generate with structure or emotion. Maybe do some sort of wild combination of measuring the tension with the tension model and getting the long-term structure in there by using word-to-vector with a lot of possibilities there. Okay. Right. I don't want to keep you too much longer. I think there's a lot happening in the field right now. We can do everything with deep learning. Well, actually, that should be a question. Can we do everything with deep learning? I think we should be careful, because we shouldn't forget all this musical history. That's also why I put so much emphasis on like the rules and showing you the sort of things that have been done in the past. I think if you're just a neural network engineer trying to generate music, you might not get too far unless you're willing to also read up a little bit on musical intervals and sort of the history of what's been done in this field. Okay. But there's two very obvious challenges remaining, so it's perfect to try to tackle. Thanks.
Okay.